Welcome back. In the last part of this section, we'll be talking about operations with functions, adding them, subtracting them, multiplying, dividing them, and we'll also be talking about domains of functions a little bit further. So we'd already introduced the idea of the domain in the previous videos. The domain, that would be the set of all the x values that we can have as our input. And sometimes we'll have things where, like I gave in the one problem, where I'll say f is a function that maps from the reals to the reals. So maybe I might tell you what the domain and the codomain are. But for the most part, you'll usually just see a function given like this, and nobody has explicitly said what the domain is. And the reason is that you would just assume that the domain is the largest set of all the possible x values that you could use. So there's lots of x values that you could put in for x. All we want to say for our domain is it will be the set that contains all the possible values that we could use. And for different kinds of functions, there's restrictions on what sorts of values of x you can use. Some kinds of functions don't have any restrictions. So for example, if I handed you a polynomial and I said, what would be the domain of this? You'd say, well, for polynomials, you can put in any value you'd like for x. You'd be able to evaluate 5x squared plus 3x plus 1, no matter what value you had for x. But for some other kinds of functions, there are restrictions. Namely, if you've got something where there's a denominator, then you know that the denominator can't be 0 because that would make things undefined. Or if you had something that was a root, square roots of negative numbers are not real numbers, so you can't have the inside of a square root being negative. These are the sorts of things you'll be thinking about when you're coming up with the domain of your function. Later on, when we start introducing things like logarithms and trigonometric functions, there'll be other kinds of restrictions that we'll be needing to think about. But for right now, these are the two main ones. That if it's an even root, square root, fourth root, whatever have you, that the inside cannot be negative, and that if you've got a fraction, the denominator can't be 0. So for this first problem, we have f of x being root of 1 minus 2x, and we want to know what the domain is. And so the first thing that I would say to myself is, I know that 1 minus 2x needs to be 0 or larger. And so that means that negative 2x needs to be greater than or equal to negative 1, or that x needs to be dividing both sides by negative 2, so that it changes the direction of my inequality. X needs to be less than or equal to a half. So that means that if we're thinking about values for x, any value for x that's larger than a half would make the inside a negative, which would mean that the square root would not be a real number. Now here I want us to express our answers two ways, one using set notation and one using interval notation. And depending on the kind of domain that you're talking about, one might be easier to use than the other. It's nice to be familiar with how to do both. So here I'm going to do it with both, but you'll see that for giving our domain in set notation, you would specify that the domain is the set of all x's such that, or with the property that, x is less than or equal to 1/2. So if I'm writing my domain in set notation, a couple of things just to remind ourselves. One, that for any set we're using curly brackets around it, so that's what my little curly brackets are. And that it's the set of all x values. We're specifying what our variable is. It's the x values. And the vertical line, we read that as meaning such that, or with the property that. So the domain is the set of all x's such that x is less than or equal to a half. Now, an easier way, I think, would be to express it in interval notation. And that would be to say, if we want all the values less than or equal to a half, that's the interval going from far left all the way up to a half and including, so square brackets around the half. For the next one, for g of x, finding its domain, I can look at this and first factor the denominator, and I can see that the denominator would be 0 in two places. It would be 0 if x were 2 or if x were 3, so we know that x can't be 2 and x can't be 3. So when we think about specifying our domain, this one, it would actually be much easier to do it with set notation. We'd say that it's the set of all x's such that x is not 2 and also x is not 3. And that would be how I would specify that it's everything else except for those two values. In interval notation, we would have to express the interval in three pieces. It's everything from the far left all the way up to 2, not including the 2, so round brackets, together with all of the numbers between 2 and 3, so from 2 to 3, not including the 2, not including the 3, and then together with all of the values that are larger than 3, everything from 3, not including it, to the far right. So this is an example of one where interval notation maybe is a little bit clumsier to use, because here our domain is really in three pieces: everything below 2, everything between 2 and 3, everything above 3. And so if we're expressing our domain in interval notation, we've got three intervals combined together. Set notation may be a little bit easier because you can just say it's everything except for those two values that we don't want. All right, so now operations on functions are pretty much what you'd expect them to be. So if somebody says, for example, what is f plus g, they're asking you to take the function f and take the function g and add them together. So nothing really surprising about those. The one thing that we will have to say is just a note about the domains for those functions, because of course, if f is a function and g is a function, then f plus g should be a function, and f plus g will have some sort of domain. And the thing that we want to know is, how do the domains for f and g relate to the domain of f plus g? So some things are nice, that for addition, multiplication, and subtraction, the domains of those combined functions would be the same as the domain of f and g combined. Whatever values happen to be in the domain of both of those original functions of f and also g, those will be inside the domain of f plus g, f minus g, f times g. So kind of nice, sort of the domain carries over. For f divided by g, you would have to have the values of x being in the domain for f. They would have to be in the domain for g. And of course, because we're thinking about something where there's now a denominator, you'd want that denominator to not be 0. The one important part here, and this is something I do want to make a little note by, is that no matter how things turn out, no matter how things simplify out, if you have something where f is originally undefined for a value of x, or g is originally undefined for some value of x, then f times g, f plus g, f minus g, f divided by g, that those would all be undefined for those values of x, no matter how things simplify. And also f divided by g would be undefined whenever g is 0, even if things canceled out. So as an example of what I mean by that, if you're thinking about the two functions y equals x and y equals 1 over x, if I ask you to calculate f times g, that would be taking my function f of x and multiplying it by my function g of x, or getting x times 1 over x, and the x's cancel and give you just a nice little 1 as your result. Now, G was originally undefined when x was 0. X could not be 0, otherwise g of x would be undefined. You might take a look at this final result and say, oh, we can put in a 0 for x just fine here, because of course there's no x's, so any value for x would be good. Except you'd be wrong, because remember, to get to this stage, we had to have x times 1 over x, and the 1 over x would have been undefined if x was 0. The canceling that we did only really makes sense if 1 over x is not undefined, and for it to not be undefined, x would have to not be 0. So although the final result, f times g, is equal to just 1, you might think it's defined for all real numbers, it also would be undefined for x being 0. Because if g was undefined when x is 0, then anything involving g would be undefined when x is 0. So something for us to keep in mind as we go forward. We're going to have to think about where were the original functions defined. So even if things cancel out, that's not going to fix our problems. So here we've got 3 functions. 2 of them are relatively nice. F of x and g of x are just nice little polynomials. And m of x, we've got x minus 3 over x squared minus 4. The first thing that we can see here, just to mention a couple of points before we go further, for both of these, f and for g, there's no restrictions on the values for x. So the domain for f and the domain for g would be all real numbers, or in other words, everything from negative infinity to infinity. M of x, on the other hand, if you were to think about factoring out the denominator, you could see that there's 2 values that you would not be able to put in for x, which would be positive 2 or negative 2. And so both of those would have to be excluded from the domain of m of x. So this is something that we'll need to keep in mind, that if we're doing anything involving m of x, even if things cancel, we'll still have to restrict x being 2, and we'll have to restrict x being negative 2. Okay, so let's start with the first one. We're looking for f plus g, and that would be f of x plus g of x. And that's easy enough to do. We just take f of x, which is 6x minus 1, and we'll add g of x, which is x squared minus 5x plus 6. And then we'll just add everybody together. So we'll have x squared plus x plus 5. And since this is made out of f and g, and f and g, their domain was all real numbers, then f plus g should also have a domain that's all real numbers. For f minus g, so we're taking function f, which is 6x minus 1, and we're subtracting g of x, and we're simplifying. We'll have negative x squared plus 11x minus 7. And again, this was made out of function f and function g, and those both have the domain of all real numbers, so f minus g, its domain should also be all real numbers. Okay, let's look at this next one, gm. So g times m, or g of x times m of x. And g of x, that was x squared minus 5x plus 6. And m of x, that was x minus 3 over x squared minus 4. And if I just clean things up a little bit, g of x factors really nicely. X minus 2, x minus 3. And m of x, the denominator, factored as x minus 2x plus 2. And you can see that the x minus 2's are going to cancel just nicely here. So g times m should simplify to give me x minus 3 times x minus 3 in the numerator, and in the denominator x plus 2. So now, if we're thinking about our domain, you would say, well, for sure, it's pretty clear looking at this that x cannot be negative 2. And that's because if you had a negative 2 for x, this for sure would be 0 in the denominator and it would be undefined. And if you felt like you should stop there, you would be wrong. Because, of course, remember that our domain is not just what are the values that we can't use when we've simplified and it's all cleaned up and looking nice. It's also what are the values that we have to restrict because we couldn't use them from the start. Remember that m of x has something where the denominator would be 0 when x is 2 or negative 2. So even though the x minus 2's happen to cancel at this part, that doesn't mean that 2 is now available for us as a value for x. We would still have to say that x cannot be positive 2 because x being positive 2 would have made the original function of m of x undefined, which would have made g times m undefined, which would mean that this final result would be undefined. Anything that makes any of the original functions undefined would be values that would make that product undefined. So since m was not defined for 2 or negative 2, that means g times m is also not defined for 2 or negative 2. So here I've chosen to express my domain in set notation, the set of all x such that x is not negative 2 and it's also not positive 2. All right, last one to work on here for this example, we have g divided by m rather, g of x divided by m of x. And so just as a reminder for the domain, we'd be thinking about what are the values that are not excluded in g, not excluded for m, and also values that don't make the denominator, that don't make m of x equal to 0. So in a way, you could actually figure out your domain before you simplified. And I might consider doing that here. I'm going to get myself started, though. G of x, that was the x squared minus 5x plus 6. And m of x, that was the x minus 3 over x squared minus 4. So if you're thinking about the domain, and I'm going to write this up top, remember that we would have to exclude any values that make g undefined, any values that make m undefined, and also any values that make m equal to 0. And so one thing we know, of course, g is fine. G is defined everywhere. That's as nice as it's going to get. But for m, there's two problems. M as it's originally defined would be undefined when x is 2 or negative 2. That would make that 0 or that 0, which would make this little fraction undefined. But we also have a problem of x being 3. If x was 3, then that would make that 0, which would make this whole expression 0, which makes the denominator of this big fraction 0, which also makes things undefined. So if we're thinking ahead of what our domain should be, I'm expecting that for my domain, that x should not be 2, because that makes m undefined. It shouldn't be negative 2, because that also makes m undefined. And it shouldn't be 3, because that makes m equal to 0, which makes g divided by m undefined. Okay, so last thing to do, we're going to actually simplify this now. We have g divided by m. We're dividing by this fraction. That's the same thing as taking g of x and multiplying it by the fraction that's been flipped. So x minus 2x plus 2 over x minus 3. And some things cancel. The x minus 3's cancel. And we're left with x minus 2 times x minus 2 times x plus 2. or in other words, x minus 2 squared times x plus 2. And we can see here that, yes, there's a good reason why 3 couldn't be used, and you can see it here on this line, that if you allowed for x to be 3, then you'd be multiplying by something undefined. And of course, that's not so good. So even though the x minus 3 is canceled, you still have to restrict x being 3, because at some stage in the proceedings here, if you put in a 3 for x, for example, even at this line, you would have a fraction where the denominator is 0, because you'd have 0 over something in your denominator, which means the denominator would be just 0 itself. So for this function, g divided by m simplifies to give me x minus 2 squared times x plus 2, and my domain is all of the x's except for 2, -2, and +3.